talking about low energy experiments in particle physics, results, and prospects. Ele tá ligado?
Alô? Pronto. Thank you. Hi everybody. My name is Diego Cogollo, and today I'm going to tell you about some low energy experiments in particle physics, some results, some prospects. Okay. The first of the experiments that I want to tell you is the KK collider. The KK collider is an electron-positron collider, and this experiment was designed to produce exclusively beam mesons. The main objective of this experiment was create beam mesons, and it was projected to achieve a luminosity with this value, a high number, and it was achieved in 2003. The process that the KK collider generates is the collision of an electron and a positron, and generating an upsilon particle, and the upsilon particle travels, and after a time it decays into a pair of beam mesons. The Belle detector is the detector installed in the KK collider, and the main objective of the Belle detector was to prove that in the decays of the beam mesons, the CP symmetry is violated. And the collisions generated in the KK collider are collision of 8 JeF electrons and 3.5 JeF positrons. For this reason, the upsilon particle generated is generated with a momentum of 2.5 JeF in the direction of the momentum of the electron. And after generated, that particle decays into a pair of beam meson particles. Then the average luminosity of this experiment was this value, and the cross-section of the process electron-positron generating upsilon particle traveling and decaying into beam mesons is of approximately 1 nanobar, and for this reason, for a period time of collecting data of approximately 4 months or 5 months, that is this time in seconds, they produce approximately 10 million of BB pairs. Okay, then the Belle detector record this data and analyze the decays of these particles and prove that the CP, the symmetry CP, is violated in the decay of the beam mesons in the same way that is violated in the decay of the counts, neutral counts. Then for this reason, the Belle detector proved that CP is violated in the decay of the beam mesons, and in parallel with the Bar collaboration. It was in 2001, and 7 years after, the Kobayashi and Masukawa was awarded with the Nobel Prize. This is a poster of the Belle collaboration. Okay. The Belle collaboration, as I said, the main objective of the Belle collaboration was proof the CP violation in the beam meson decays, but also works in other projects because they have a lot of data recorded. And one of these projects is the search for this particle, this pseudoscalar particle. As we know, the electron-positron collision generates an upsilon particle, and the upsilon particle travels, decays into a pair of beam mesons. And one possible decay of these beam mesons is the decay into a count, neutral count, and into this scalar particle that after decay into a pair of leptons or hadrons. Okay. Other project of the KK collider is the search for a light Z prime gauge boson. Okay, but in this case, the process is different. The process is the collision of an electron and a positron, annihilating each other, generating a photon, and the photon decaying into a pair of leptons. And from one of these leptons is radiated a Z prime boson, and the Z prime boson decaying into a pair of neutrinos or a pair of dark matter particles. In these two projects, they set constraints in the plane, in the coupling of the particles and the mass of the particles. Other project that the Belle detector works is the search for this light scalar particle. In this process is the collision of an electron and a positron, generating a gamma or Z particle, and this gamma or Z particle decaying into a pair of tau leptons. And from one of these tau leptons is radiated this scalar particle that after that decay into a pair of leptons, or electron positron, or mu plus mu minus. Okay. They look for this hypothetical particle. The research was based in this the research. Okay. The research of Belle was based in this scalar particle, this hypothetical particle, that has kinetic energy, mass, and is an leptophilic particle, and interact with the lepton in this way, in the same way that the Higgs boson interact with the fermions. Then, for this reason, the Belle collaboration search for. For this reason, the channel that they study is this channel, because if the particle interact strongly with the tau, then this channel is the main channel, the channel that produces more particles. Okay. Oh. The data used in this analysis was recorded by Belle experiment, which operated until June of 2010, and this is the value of the luminosity. Okay. And the signal of this process is a pair of taus. We have here the boson decaying into a pair of taus, and from one of these taus is radiated a scalar particle that decays into a pair of leptons. Then the signal is a pair of taus and a pair of electron, positron, or a pair of mu minus mu plus. Okay. However, no signal was seen different from the background in this study, and in absence of signal, the Belle collaboration imposed upper limits in this cross section. Okay, this was a published paper, and okay, we use this report. We use this work of the Belle collaboration, but different from them, we image the existence of an hypothetical scalar, but different from the scalar that they study, this scalar interact with an universal coupling lambda. Then, in this case, if this scalar now interact with an universal coupling lambda, then it is important to study all other processes. For example, electron, positron, S, lepton, and mu minus mu plus, lepton, okay? This was our objective, to study all these processes, because in this case, all these processes have the same weight, are same important, okay? Then our idea, firstly, we just work with this diagram. Okay, firstly, we just work with that diagram. We use the reported data of the Belle collaboration, and we simulate the cross-section, this cross-section, E minus E mass generating tau minus tau mass S, and S decaying into a pair of leptons. Then here we can see that this line, this red line is the cross section of the hypothetical scalar, and this blue line is the observed or the data published by the Belle collaboration. Then in this diagram, in this figure, we fixed the value of the lambda coupling, and then in this way we run for different values of lambda and set our limits for the mass of this particle. Then this is the constraints we obtain in the lambda ms plane. We compare with the data. Okay, this scalar particle with this interaction also generates a contribution to the muon anomalous magnetic moment and for the electron anomalous magnetic moment. It is important to say that in this figure we use the value before the new published data of the muon anomalous magnetic moment. Okay, this is a paper of the last year. Then the new result of the muon anomalous magnetic moment is from June of this year. Okay. Okay, the other experiments that I want to tell you is not a specific experiment, but it's a family of experiments. Are the parity violation electron scattering experiments that are basically, the idea is basically accelerate electrons with an specific helicity and scatter off from different targets, mainly hadrons, but not necessarily hadrons. Then the idea is to accelerate electrons and scatter off from, maybe you can think as fermions, but fermions may be electrons, may be quarks that compose the hadrons. Okay. The observable in this kind of experiments is this quantity that I will call the asymmetry. The asymmetry is defined as the difference, is proportional to the difference of the cross-section for when the electrons are polarized in the left helicity state and for when the electrons are polarized in the right helicity state. And the differential cross-section must be calculated in this way. It's a very complex problem, really very complex problem. But basically we can see that the cross-section depends of this quantity. The cross-section depends on n gamma plus mz star n gamma plus mz, okay? For when the electrons are prepared in the left helicity state, and minus for when the electrons are prepared in the right helicity state. And it is important to say that this asymmetry is different from zero when we consider only the standard model. Obviously, this asymmetry is different from zero because we have here the exchange of the Z boson. If we consider only the exchange of the photon, obviously this asymmetry is equal to zero because the photon is a parity conserving interaction. That it means the photon interacts with the same intensity with left-handed electrons and right-handed electrons. But the Z boson not. The Z boson is a chiral interaction. Then the Z boson interacts differently with the left-handed electrons and with the right-handed electrons. Then for this reason, in the standard model, if we consider just the standard model, this quantity is different from 0. And when you expand this numerator, at the end of the day, you can prove that this asymmetry will be proportional to something of the form of this way. Okay, that it means that this asymmetry basically depends on the interference terms of the gamma and the Z boson. Okay, and here it's important to say also that these kind of experiments are studied using formulas of the effective field theory, using effective Lagrangians. And at the end of the day, this process can be represented if we consider, because the Z boson is the generator of the symmetry, then we can consider that this asymmetry is generated when we are exchanging a Z boson in the way that this electron, the axial coupling of the electron is considered in this vertex, and in this vertex is considered the vectorial coupling of the fermions that compose the target, okay? That we call F generically. Then this is the Lagrangian that we use to study this kind of processes, okay? Then it is important to see here that this quantity, this vectorial coupling of the Z boson with the target generates that this Lagrangian depends of the weak charge of the particles. The weak charge is the weak charge of the target is of any fermion. The weak charge is the constant that with the Z boson couples to the fermion. Then you have a fermion here, you have the Z boson interacting, and this vertex, the vectorial coupling of this fermion with the Z boson is proportional to the weak charge. In analogy with the photon, when we use this vertex, and we have here the photon, this vertex is proportional to the electric charge of the fermion. Then we can see here that this effective Lagrangian at the end of the day measure the weak charge of the targets, okay? Here I present the values of the weak charge of the proton and the values of the weak charge of a hadron, okay? A generic hadron. Okay. For example, there is, I don't remember the name of the experiment. I guess the name is the Moller experiment that measure the symmetry when you use electrons polarized with different polarizations. When you use electrons polarized with left helicity and right helicity and calculate the asymmetry, when the target is an electron, the Moller collaboration published that the asymmetry at the regime of low energies can be written in this way, okay? Then it's proportional to the weak charge of the electron and depends also of these parameters where Y is the difference of the energies of the initial and final electron. Okay, and here I'm going to talk about a specific experiment that is the K-weak experiment. In the K-weak experiment, the target are protons. Okay, then the K-weak collaboration, the K-weak experiment, use electrons with this low energy, 1.16 GeV of energy, at the Thomas Jefferson National Accelerator Facility, and that electrons are scattered off the target of protons, a target of protons. And the symmetry measured by this collaboration is given by this expression. And here it's important to say that in the case that we are working with hadrons, we introduce here a factor, a correction factor, obviously because the hadrons are composed systems, okay? Then depending of the energy of the electron, then you can see the internal structures of the hadrons, okay? This term is this depends on the form factors of the proton, okay? But you can see that in the limit that Q squared, that is the momentum transfer, going to zero, then this term can be disregarded, and the symmetry just depends on the weak charge of the proton. In this way, you can measure the weak charge of the hadrons. Okay. Okay, as I said you, at the, up to now, I just told about the contribution of the standard model, but it's possible that experiments can measure the contribution of new physics. Okay, for example, if you have Z boson, a new light Z boson that possess this general interaction with the fermions, then obviously this new Z boson generate an effective Lagrangian that will depend of the axial coupling of the electrons with this particle and the vectorial coupling of the target with this Z boson. Okay, then if you add these contributions at the end of the day, you can measure a chief of the measure of the weak charge. And here is we have an important point. The important point is that this change of this chief of the weak charge can be codified as a chief of the Weinberg angle. Okay, the idea in these papers is codify this chief of the weak charge as the chief of the Weinberg angle. We know that the measure of the Weinberg angle depends on the energy of the experiment. Then, okay. Then here I'm going to tell you about some specific family of models that possess this kind of particles that can contribute to the measure of this chief on the weak charge or the weak charge and or the Weinberg angle. Okay, this kind of model are the two Higgs doublet models, and we work with a specific model of this family of models that is a model with two doublets, but just one of them couples to all the particles. Okay, this is to avoid the flavor changing neutral currents, and from the theoretical point of view, you can generate this model, you can construct this model if you suppose that the charge of the doublets is different, because if the charge of the doublets is the same, you can generate a term Q phi1 D, Q phi1 U if the charges are the same. Then it's mandatory in these models that the charge of the two doublets must be different. Okay, and then this Lagrangian generates a family of models. All of them are free anomaly models. Okay, and here we present summarize of these kind of models. We have and here it's important to say that these models are constructed with that quantum numbers of the right-handed quarks. The quantum number of the right-handed quarks, this quantum number is the quantum number associated to the U1X group. Then the charge of the right-handed quarks for this group is U, and the charge for the D right-handed quarks is D, and the other particles, the charge of the other particles are function of these numbers. Then all these models are free anomaly models. And it is important to say that after the spontaneous symmetry breaking, the Z boson gained a master, but I don't know, it mixes with the new gauge boson associated to this new gauge group, okay? Then this mix is, we can diagonalize this equation using this transformation, and at the end of the day, we obtain this neutral currents for this model. We recover the standard Lagrangian of the Z boson, and for the new Z prime boson, we have this important feature for this scalar. We can see here that the Z prime boson can have behaviors of a dark photon, okay, because this scalar interact in the same way that the photon, but the charge is modulated by this factor epsilon. Also, is called the dark Z boson because this scalar interact with the particles in the same way that the Z boson, also modulated by this factor Ez. And moreover, when the charge of the particles, all the particles, are different from zero, these two terms are for the case when the charge of all particles is equal to zero. For when the charge of the particles is different from zero, then we can add these two contributions, okay? At the end of the day, we have a very rich model. Finally, we can write the interaction of this new Z prime boson in the way that we can use for the calculation of the chief of the weak charge, or that it means we can write the interaction of the Z prime boson in this way, separating the vectorial coupling and the axial coupling, okay? Here I show you the example of how can we write the Z boson current as function of the charge of the particles. That it means for the charged leptons. That it means that the interaction of the charged leptons with the Z prime boson depends, it's model dependent because the charge depends of the model, okay? Then in this way we can derive constraints on these models using this kind of Lagrangians, as I said. Okay. As I said, the chief of the weak charge can be codified and as a chief of the Weinberg angle, and in this kind of model, the chief of the and in this kind of model, we can write the chief of the Weinberg angle as proportional to these quantities. This is a function of the propagator. Here is important because the propagator it must be taken into account because the mass of the Z boson is a mass in the range of the, I don't know, Jeff, okay? Then it's different from the case of the standard Z boson. The mass of the standard Z boson is about St. Jeff, 100 Jeff, sorry. Then in the term in the propagator depends only on the mass of the Z boson. In this case, it's necessary to take into account the momentum transfer and the mass of the new gauge boson, okay? Then, okay, in this paper, this was other paper of our group, we derived the constraint on this epsilon particle using the measure of the Weinberg angle and different scale of energies. Okay. And finally, I want to tell you about this important topic that are the rare kaon decays. I'm going to tell you about the rare kaon decays because this problem is related to other kind of experiments. What kind of experiments? The kind of experiments that use protons to collide with fixed targets, as beryllium, for example. Then these processes are governed by the strong interactions. Then, as these processes are governed by the strong interactions, the main products of these collisions are kaons. And the kaons decay mainly into muons and neutrinos. Okay, then this is the way that the Fermilab produce the muon neutrinos that use to study the evolution and oscillation of these neutrinos. Then other experiments use protons, accelerate protons to collide with fixed targets to generate kaons. Then this rate decays, okay, the main decay of the kaons is this one. Then the rate decays can be considered when then we have a kaon decaying into a neutrino of the muon and a muon. This is the main decay, but rate decays can be considered as the radiation of one particle here from the muon leg, and that particle decaying after that, okay? Then, for example, if we have the rate decaying kaon, neutrino, muon, neutrino, neutrino, or neutrino, muon, electron, positron. And for this rate decays, we have constraints, published constraints, and we can use different models to constrain these models, okay? Then we did a paper recently, and we used this width that was calculated in this paper, is a data group, and using this information, we use the experimental published results to constrain the parameters of this kind of model that I told you. Okay, one of the experiments is the NA62 collaboration that constrain the branching of the kaon to be less than this number. Okay, then we interpreted this rate decay as the emission from the leg muon of a Z prime boson, and after that the Z prime boson decaying into a pair of neutrinos. Okay, then we consider that the Z prime was generated on shell, and after that decay into a pair of neutrinos. Okay, and we, at the end of the day, we realize that we need to find the analytic way, the analytic form of these two terms. And here we construct the analytic terms of these two terms. This is the way the Z prime boson decay into a pair of fermions that we have the current and we can calculate because we know the vectorial and axial couplings. And in the same way, using this constraint of this experiment, we use this constraint to also constrain the mass and some quantities of characteristics of these models. Okay, in this experiment, it is important to say. it is important to point out that this equation 30 here, this constraint here, was derived for an invariant electron positron mass greater than 145 MeV. Then this constraint applied just for masses of the Z prime boson greater than this value. Then finally we calculate these constraints. We use these constraints to constrain these quantities that are characteristics of this model, the coupling constant of the Z prime boson as function of the mass of the Z prime for different models. These are, as I show you in the table, we have a family of models, all of them anomaly free. Then here we have the constraints, all the area above the lines are forbidden points. Okay, here is not so important. And in conclusion, in summary, ray count decays, Belle and parity violation electron scattering constitute a great laboratory for probing like hidden particles. Okay, then it's important to be aware about the main properties of all these experiments to use the theoretical models to constrain the parameters of these theoretical models. Here the reference, and thank you very much for listening.
Questions?
Wait a second.
Oi. Diego, I have two questions. The first one is, the last plot you showed, there are some very high values for the tangent of beta. And usually, when they are very high, there are a lot of constraints over this parameter, right? Because it's the mixing between the charged scalars, right?
Yes.
The goldstone. So, are you considering these limits? And my second question is, how this experiment, like Bell, can differentiate between 3 neutrinos in the final state or 1 neutrino in the final state? Because you are showing us that this decay on the zeta prime into two neutrinos could induce new physics, right? So what is the difference on a detector? Because it seems to me that it is more kinematical stuff, but the background is very high. So so I have these two questions.
Okay, I really don't know because I really don't work in these constraints derived from Belle collaboration. I know that the study that they did is about the constraint of the Z prime boson decaying into dark matter or decaying into neutrino pairs, but I really don't know nothing about the specific about that specific study. And about the tangente of beta, that is the reason of the vacuum expectation values, I was certified that the values of tangente beta greater than 10 are free for these models. I don't remember specifically using the constraints of the mass of the charged scalar, but I don't remember.
Yes, there are 4 types of 2 Higgs doublet model, right? The X, the U, the 1 and 2. Type 1, understood, okay.
The type 2 is really highly constrained, but the type 1 is...
Okay, I see. Thank you.
More questions? Just check online if someone said something.
Okay.
Okay, let's thank Diego again.
Thank you.
And our next speaker is João. And